The vector product. This is also sometimes called the cross product, but while it looks similar to the scalar product, it is not the same and must be calculated in a different way, and we're going to look at that here. So we write V is equal to A cross B. Remember, with the dot product, we write A dot B. That's why it's called the dot product. Although its real name, of course, is the scalar product. This one is the vector product, and the cross is the operator. So, V turns out to be mod A, mod B, sine theta, and then n hat. N hat is a unit vector which is perpendicular to both A and B. And this is why this is so useful. If we have a vector A and a vector B, and we do the cross product, then we end up with a vector that goes this way, which is perpendicular to both of these other vectors. In addition to that, if you think about mod A, mod B, sine theta, if we have these vectors forming a parallelogram here, so that this one is also A, and this one is also B, AB sine theta is the area of this parallelogram. So if we do half of the magnitude of the vector product, we get the area of a triangle like that, formed by A and B. So it's just a couple of ways it's useful. So the vector product of A, which is A1i plus A2j plus A3k, and B, which is B1i plus B2j plus B3k, is given by this. It's fairly important to note here that this one is positive, as is this one, and this one has a negative in the middle. This looks tricky to memorize, and so below I'll show you an easier method to find it. It requires us to work out the determinant of a 3 by 3 matrix. Now this is something that you may actually not know, but it's easy to pick up. So what we do is in the top row we put I, j and k, and then in the middle row we put A1, A2 and A3, that's the coefficients from the vector A, and in the bottom the coefficients from the vector B. To calculate the I component, what we do is we put a line through the top and a line through the column that contains the I component coefficients, and then we work out the 2 by 2 matrix that's left. So we do A2 times B3 and then B2 times A3, which we can see we've got here. So that gives us that one. Then for the j component we cross out the top and the middle column. Now with this one we have to remember to put the minus here, but other than that it's A1 times B3 and A3 times B1. And then for the, yes, I just made a little arrow here just to note that we need that minus on the j component. And then for the k component we cross out the row and this column and work out the 2 by 2 determinant like so. It seems long-winded, but with practice this can be done quite quickly. So, as I just said, it seems a long-winded method. The advantage is the pattern's easier to remember in a test or an exam situation than trying to actually memorize this. It's worth noting the following things. Mod of A cross B is mod A mod B sine theta. We pointed this one out before, where theta is the angle between A and B. So I'll just go through that again. that if we've got vectors A and B here, then crossing them and just having the modulus of that gives us this, which would be the area of this parallelogram. And so half of it would give you the area of the triangle formed by the two vectors. The vector A cross B is perpendicular to both A and B. We talked about that as well. So if you cross them, it produces a vector here, which is at right angles to both A and B, and that has obvious implication when we come to planes. A cross A is equal to 0 for any vector A. This is a bit like, we know that the dot product, A dot B, is equal to 0 if they're perpendicular, and that one of course is because the cos of 90 degrees is equal to 0. Well, here if you've got A cross A, you've got sine theta here, and of course sine of 0 is equal to 0. A cross B is equal to 0 implies that A is equal to 0, or B is equal to 0, or that A and B are parallel. They don't have to be in the same direction because the sine of 180 degrees is also 0. A cross B is equal to the negative of B cross A for all vectors A and B.